Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. So today I thought I'd make a video on Bayes' rule, not because this is a particularly complicated rule or a very difficult concept to understand, but actually, believe it or not, I had trouble for the longest time in understanding why the formula works. And it turns out that is because I had just thought of it as a formula but never really tried to visualize it. And of late, I've also realized that Bayes' rule is not important just in foundational mathematics, but it's also become so important in today's AI boom, where we have so many probabilistic machine learning models that really, whose underpinnings are really based on the Bayes' rule. And so I think it's worth exploring this concept in a little more detail today, and in probably a more visual way that actually changed my understanding of the rule and made it such that I would never forget it. So that's enough of an introduction. But what exactly is the rule? So this is how I was taught the rule. So probability of A given B. So this is the notation for given. So probability of the event A given that B has occurred is the probability of A intersection B divided by the probability of B. So this is how I learned the rule first. And of course, you have a bunch of symbols here and it looks not very intuitive to me at least. And for so many years, you won't believe it, I never really understood why this rule works. So I had just sort of memorized it just so that I could apply it. I knew how to apply it, but I never really understood how this formula came to be. And sometime back, I was exposed to the idea of visualizing probabilities, and I think that completely changed my perspective. So I wanted to share that so that we think of probabilities not just in terms of abstract symbols, but actually in terms of visualizations. So let me scroll down a little bit and let's draw a representation of probability first. So let's say we have the sample space that is represented by this rectangle. So the rectangle represents the set of all possible outcomes, and let's say A is represented by this circle. I want to use different colors for each of these so that we can keep track of them easily. And let's say B is represented by a rectangle that looks something like this. Okay, so I'm being really perfect today with my symbols. So this is the event B. The event B is represented by the rectangle, and the event A is represented by the circle. So what we want to do is think of the probability of event A and B not just as a formula, but actually in terms of areas, right? So what do I mean by that? Let's write down a few things, and hopefully it will become clear as to what I'm trying to say. So before that, I want to just create like a small legend. So the rectangle represents event B. The circle represents event A, right? And let me shade this part in brown. Okay, so the brown semicircle represents the area that lies in both A and B, right? And by definition of intersection, this is A intersection B, right? And what does the overall rectangle represent? The bigger rectangle. The bigger rectangle represents the sample space. So let me call that S. So that's the set of all possible outcomes. And now let's write down a few equations. And I think this is going to be really interesting for those of you who haven't seen it before. And for those of you who have already been exposed to this, hopefully this is a good refresher. But to be honest, this completely changed my idea of Bayes' rule once I was exposed to this. So let's write down the first equation, which is the probability of A, right? So the probability of A, so let's say you're throwing darts and like the darts are just uniformly going and hitting this dartboard. So what is the probability that a dart lands in area A? So well, if the dart has equal probability of landing everywhere, then the probability that it lands in area A is nothing but, okay, now I have to be careful here while keeping track of colors. So if the probability per unit area is constant, which I'm assuming it is, then the probability, if I throw a dart on this dartboard, the probability that it lands in the circle A is nothing but the area of the circle A divided by the area of the sample space, right? So that is probably not very new to most of you. I'm sure most of you had this idea, definitely. And similarly, the probability of event B, let me write this first, is the area of rectangle B divided by the area of the sample space. Alright, so this is very, very simple and straightforward so far. But what is interesting is that when we try to understand what is the probability of A given B, right? So now we are slowly converging on the core idea of this video, which is to understand the formula, that Bayes' rule. At least the way I was exposed to it was just as a formula. But what is the probability of A given B? So let's just look at the English interpretation. What is the probability that A occurs given that B has already occurred, right? So what is the probability that, let's say, so I'm throwing darts on the dartboard, correct? What is the probability that the dart lands in A given that it has already landed in B, right? So how do we think about this? So let me pause. So I encourage you to pause for a second here, and based on the English explanation of A given B, I encourage you to try and write the expression for P of A given B in terms of ratio of areas. So hopefully you're done trying. So let me repeat what I just said. So we're looking at A given B. So I'm throwing darts, and what is the probability that the dart lands in A given that it has landed in B, right? So if the dart has already landed in B and it should also land in A, then it has to land somewhere in the intersection, correct? So that is the first step. And it has to land in the intersection, but I've already told you that it has landed in B. So basically it is somewhere, the sample space in this particular case, so maybe sample space isn't the word for it, but the set of outcomes here is B, the set of all possible outcomes given, because we are told that B has already occurred. So B has already occurred, right? So that means the set of all possible outcomes is basically the area of B, and the probability that it lands in A, given that it has landed in B, if it has to land in A, given that it has already landed in B, it has to land in the intersection. The dart has to land in the intersection. And so essentially we are almost done. So all we have to do is a little bit of modification here. So it's the ratio of the semicircle divided by the ratio of the green rectangle. So this can be slightly modified into a different format. So this can be rewritten as the ratio of the semicircle divided by the ratio of the bigger rectangle, and this fraction is going to be divided by another fraction. And many of you may have already realized where this is going, but this is divided by the ratio of the green rectangle to the bigger rectangle, right? And what is let's see, we are almost at the end. What is this expression here? Well, this is, if you can just pattern match, this is the probability of B, right? And what is this expression here? So it's the ratio of the semicircle to the ratio of the bigger rectangle, right? So that is nothing but the probability that the dart lands in the semicircle, right? And that is nothing but the probability. So this part is nothing but the probability of A given B, right? So we are almost at the very end here. We have completed our highly informal proof of Bayes' rule. So the probability of A given B, which is the ratio of the semicircle to the green rectangle, is nothing but the probability of A intersection B divided by the probability of B. Alright, and we are done. So this completes a very informal and non-traditional proof of Bayes' rule. But I really want to mention that for many years, this is how I had somehow just remembered Bayes' rule without really understanding what it means. But probability, like one way to visualize it is to think of it as darts being thrown on a dartboard. And if we think of it that way, Bayes' rule goes from being just a formula to something that has a visual interpretation. And I always felt that, understanding a formula makes a big difference because you are no longer just applying it, but you understand it from first principles. So I hope you found this video useful, and I hope next time you apply Bayes' rule, this video comes to mind and you think of it not just as a formula, but as darts being thrown on a dartboard. With that, I'll see you in the next video. Bye.